Welcome back to our discussion on combined gas vapor power cycles. What we want to do today is to basically discuss this concept of combined gas vapor power cycles, which is one of the last concepts to increase the efficiency of power cycles. And so let us begin that by talking essentially about gas power cycles. So we have been talking about gas vapor power cycles for quite a bit. And what we understand is that the turbine inlet temperatures for gas turbines are much higher than the average turbine inlet temperatures for steam turbines. Essentially, when we talk about gas turbines, the turbine inlet temperatures have reached as high as about 1400 degrees Celsius as compared to steam turbines, where the turbine inlet temperatures are around 600 to 650 degrees Celsius. So you can see this is a very big change. And because of this very huge difference, because of very high temperatures for gas turbine cycles, their efficiencies are relatively higher as compared to steam turbines. And this essentially comes from the basic Carnot efficiency formula, which says efficiency is 1 minus Tc by Th. Now, as we have discussed in the class, we don't follow this formula specifically when we are dealing with Brayton cycle or Rankine cycle. This formula simply provides us the direction. And as long as you go to very high TH values, you're going to increase the efficiency for the same value of TC. Now, the good thing about gas turbine is that we have been able to increase TH quite a lot. I mean, 1400 degrees Celsius is a very high temperature. And this has essentially increased the efficiency of gas turbine cycles over the past 20-30 years. Now, the problem with gas turbine cycles, especially in their when they're operated on their own without any other combination, is the fact that the temperature at which the hot gases come out from the steam turbine, the gas turbine is still very high. We're talking about gas turbine exhaust temperatures being around 500, 600 degrees Celsius. And this means that TC is, still on the higher side. For us to achieve higher temperature, higher efficiencies, we got to bring down this TC. And one of the smartest ways of bringing down the TC is basically by combining a gas power cycle with a vapor power cycle. Okay, and let's see how that all works together. So this is a schematic showing you a gas vapor power cycle, a combined gas vapor power cycle. Let's look at how this things work. So you have the air entering the compressor of a Brayton cycle or a gas vapor power cycle. Usual conditions 300 Kelvin, 1 atmospheric pressure. It gets compressed, comes out at higher temperature and higher pressure. Then it goes through this combustion chamber where a lot of heat is added essentially from an external source, the way we model it. And basically we have hot gases at temperatures approaching 1425 degrees Celsius going and expanding within the turbine. So this is a very high temperature, and because of and this essentially forms as the upper limit, or this forms the average temperature of heat addition, right? So now the gases expand and come out at state 8. Now at state 8, the gases are still hot. So instead of rejecting them into the atmosphere and wasting all that thermal energy available in the hot exhaust gases, what we do is that we send them through a heat exchanger. Now, this heat exchanger is called a heat recovery steam generator. And the reason it is called a heat recovery steam generator is because it does exactly that, in the sense that it recovers the heat from the exhaust gases, hot exhaust gases coming out from a gas turbine, and it transfers that heat to the liquid water that's coming in at a high pressure, and it converts that liquid water into steam. So essentially, it recovers heat from the hot exhaust gases from the gas turbine and uses that to produce steam or generate steam. And that's essentially happening through the heat transfer from the hot gases to the cold water. And so once you generate steam, then you operate the usual Rankine cycle. So the hot steam at already high pressure because it's being pumped. So high pressure, high temperature steam, 620, 630, whatever degrees Celsius, it enters the turbine, produces some work output for us. So we have two turbines producing work output. One is the gas turbine and the other one is the steam turbine. And here then we send this uh, steam, which is at, essentially a saturated mixture at much lower pressure and temperature or much lower enthalpy. We send it through the condenser where we reject it and convert it into saturated liquid. So this is essentially uh, how this entire process works. All right. So uh, the key point here is that what we are doing is very simple. What we are doing is we are mainly adding heat at a very high temperature let's say around 14-25 degrees Celsius, and we are rejecting heat at a very low temperature, or mainly rejecting heat at a very low temperature, which is in the condenser. Now here, the temperature of heat rejection could be as low as 50 degrees Celsius. So instead of rejecting heat at 500 degrees Celsius, we are rejecting heat at 50 degrees Celsius. So again, when you go back to Carnot efficiency, 1 minus Tc by Th, Th was already very high because the only place where we are adding heat is in the combustion chamber right here. And this is happening at very high temperatures. Now, we had very high Tc before if you operate only gas turbine, but by bringing down Tc, by combining it with the steam turbine cycle or the Rankine cycle, we have been able to increase the overall efficiency drastically. And when we talk about efficiencies of combined cycle, efficiencies as high as 50%, 55% are the norm. There are combined gas vapor power cycles achieving efficiency of 65 to 67% already available on the market. In fact, you will have one such example to look at in terms of a GE combined vapor power cycle. So this is an excellent technology. And in terms of efficiency, it has given absolutely huge increases in the efficiency possible. Now, this is how the TS diagram would look like. We have two different working fluids. In the gas cycle, we have the main working fluid being air. In the steam cycle, it's of course steam or water. And the heat transfer essentially happens from this state 8, which is of course at a higher temperature than state 3, right? It rejects heat, it cools down, comes out at 9, and it basically helps this water, which was at state 2, a higher pressure but very low temperature. It allows us to get heated in a constant pressure process and get converted to steam. And so in terms of heat rejection, of course, the main part where we are rejecting heat is from 4 to 1, but also a tiny amount of heat gets rejected from 9 to 5. So this is essentially how this combined gas vapor power cycle works, and it's one of the most efficient power cycles on Earth. Okay, so this is about the combined gas vapor power cycles. Now we will go ahead and solve a very simple problem on gas turbine. All right, so here what we are provided is we have a gas turbine power plant which is operating on an ideal Brayton power cycle. So ideal cycle means the isentropic efficiencies for both compressor and turbine are 100%, or essentially uh, the compression and expansion process within the compressor and the turbine is isentropic. Okay, so we have an gas turbine power plant operating on an ideal Brayton cycle, has a pressure ratio of 8. So pressure ratio simply indicates the pressure at the exit of the compressor divided by the pressure at the entry to the compressor, right? So what we're being informed is P2 by P1 is equal to 8. Now the gas temperature is 300 Kelvin at the compressor inlet and 1300 Kelvin at the turbine inlet. Now, as discussed in the class, we need to be able to draw the TS diagram for a Brayton cycle. Now, this diagram has already been shown here, but I expect you to be able to draw this in an exam or in a quiz when asked. All right. So when we look at this, we know that 1 to 2 is the isentropic compression process. All right. 2 to 3 is the constant pressure heat addition. 3 to 4 isentropic expansion process, and 4 to 1 constant pressure heat rejection process. Okay, so here when we talk about the gas temperature at compressor inlet, compressor is from 1 to 2 and inlet is at state 1. So we're talking about temperature at state 1. And same way when we talk about temperature at turbine inlet, well, turbine is from 3 to 4 and the inlet to the turbine is at state 3. So we're talking about T3 here. Okay, so this is something that we should be able to understand from the question and mark it for ourselves on a TS diagram. Now, with this information, we are also being told that we can make use of the A standard assumptions and assume air to have constant specific heats, right? So if we assume air to have variable specific heats, we deal with it differently, which I will not be covering it here. Here, we will only be talking about how to deal with air having constant specific heats, which makes the analysis much more simpler. Now, for all of this situation, what we need to do is, of course, we need to determine the gas temperature at the exit of the compressor and the turbine. Now, compressor is from 1 to 2, right? So we want to determine T2, and the turbine is from 3 to 4. So we need to determine T4. Once we do this, once we determine T2 and T4, we got to calculate the backwork ratio and the thermal efficiency. Okay. Now, there's one thing that I always like to tell my students, and that is that whenever you read a question, remember the question is designed very well in such a way that to solve part B and part C, you actually need to solve part A. So you got to go through steps. Okay. So if you do not understand how to target a problem, how to where to start, well, we have already made that easy for you by giving you exactly the steps which you got to follow. So always in this kind of questions, it is a better idea to start with solving for A and then move on to B and then move on to C, because A provides you everything that you need for solving B, and B can help you with solving C. Okay, so this is how it all works. So here let us note down the assumptions and what we have. So what we need to get is temperatures at the exit of compressor and turbine, which we said are T2 and T4. This is what we need to do. Now, these are the assumptions for all cycles like this. We know that we're going to treat all the components at steady as steady state steady flow. The A standard assumptions are applicable, which basically means that you are going to evaluate CP and CV nominally at 300 Kelvin, and we'll assume constant values of CP and CV specifically for air, right? And as usual, in all of these, we expect kinetic and potential energy changes to be negligible. Now, we know that whenever we are dealing with an ideal gas, which is the situation here, we have air, which is we're going to treat as an ideal gas. So whenever we are dealing with an ideal gas with constant specific heats, and when this ideal gas with constant specific heats undergoes an isentropic process, we can come up with relationships between temperatures and pressures. In fact, temperature ratios and pressure ratios. Now, when we look at this TS diagram, we have two isentropic processes: the isentropic compression process and the isentropic expansion process. So for these isentropic processes, what we have is we have a ratio relating the temperature ratio to the pressure ratio. All right. So you cannot apply it from 2 to 3. You cannot apply it from 4 to 1. You can only apply it from 1 to 2 and 3 to 4, because it is very important for the process to be isentropic for us to be able to apply it. All right. So what is the ratio? Well, what is the relation? The relation is very simple. For ideal gas with constant specific heats undergoing an isentropic process, T2 by T1 is equal to V1 by V2 raised to K minus 1. Of course, we don't need this when we are dealing with Brayton cycle. This is more useful, let's say, in an Otto cycle. But for a Brayton cycle, this second part is very useful, which relates temperature ratio to pressure ratio. So it's telling us that temperature at state 2 by temperature at state 1, this ratio for an isentropic process is exactly equal to the ratio of pressures P2 by P1 raised to K minus 1 by K. Now, what is K? K is simply the specific heat ratio. K is Cp by Cv. And for air at 300 Kelvin, it's 1.4. Okay. Now, we have this information. So basically, when we're trying to determine the temperatures, all we need is basically the pressure ratios. And the good thing is we have been provided the pressure ratio already. So the question already mentioned the pressure ratio is 8, and we know that pressure ratio refers to pressure at the exit of the compressor, what is P2, divided by pressure at the inlet of the compressor, what is P1. And this number is already given to us as 8. Now, we already have been given T1. T1 is 300 Kelvin, which means that T2 is simply T1 times P2 by P1, which is 8, raised to K minus 1. We said K is 1.4 for air. So it's 1.4 minus 1 is 0.4 by 1.4, right? So when you substitute in the numbers, so T1 is 300, pressure is 8.4 by 1.4, T2 comes out to be 543.4. Okay, so that's one part done. We have T2 now. Same way, we know that 3 to 4 is an isentropic process, which means that T3 by T4 is again going to be equal to P3 by P4 raised to K minus 1 by K. Now, the key point here is 2 to 3 is an isentropic process, which means that P2 is equal to P3. Same way, 4 to 1 is an isentropic process, which means that P4 is equal to P1. Now, we know already that P2 by P1 is equal to 8. So since P2 is equal to P3, I can write I can replace P2 with P3. And since P1 is equal to P4, I can replace P4 with P1. And I can basically say that P3 by P4 is also going to be equal to exactly 8. And so we need to find T4. Okay, we have T3 already. T3 is given as 1300. We have P3 by P4, what is 8. So we have everything in here. We can again plug in the numbers, and T4 comes out to be 787.1. Okay, so now with this, we have temperatures at the exit of the compressor T2, and we have temperatures at the exit of the turbine T4. Right, so this is mainly the information that we sort of need. Again, just to point out, you can look that the temperature at the exit of a simple gas turbine cycle is relatively high. When we say 587, we're talking about something like 514 degrees Celsius, about the number that we discussed when we were talking about the combined gas vapor power cycle. So that's the reason it makes sense, not to reject this heat onto the atmosphere. It rather makes sense to combine it with a steam uh, turbine cycle and sort of use that thermal energy. Anyway, coming back to this question, now we have temperatures at all points, so we can basically go ahead and solve the rest of the problem. So now what we need to do is we need to calculate the backwork ratio. This was part B, right? So backwork ratio is something that you're expected to remember. Backwork ratio is simply the ratio of compressor work input by turbine work output. Now, there are two ways in which you can do this. Because we are dealing with world air standard assumptions, whenever you have delta H, you can sort of replace it with Cp delta T, as long as you're dealing with something with constant specific heats. But because we have cold air standard assumptions, this means that Cp, we can take it as Cp at 300 Kelvin, which for air is 1.005 kilojoule per kilogram Kelvin. Okay, this is something that we can certainly do. But here I just want to do the an alternate way where I want to, instead of using the Cp at 300 Kelvin, because we have all temperatures now, T1 and T2, I want to actually use the CP at T average just to make it a little bit more accurate as possible, right? Again, both ways are fine. You can take CP at 300 Kelvin if you want, but I just want to show you what happens when we use CP at T average. Okay, so now ultimately what we are looking for is we got to calculate this compressor work input and turbine work output. Now, the compressor work input per unit mass is simply equal to this is the compressor. So the compressor work input per unit mass is equal to H2 minus H1. Now, since specific heats are constant, we can write it as Cp T2 minus T1. We have T1, we have T2. Okay, on this Cp, you can certainly take it as 1.005. No problem with that, kilojoule per kilogram Kelvin. But since the temperatures are a bit on the higher side, to get more accurate numbers, I'm just going to be doing slightly long method, which is I'm going to find T average, okay, of T1 and T2. So T1 plus T2 by 2. And I'm going to get Cp at T average, okay, just to make it more accurate. Again, you don't have to do this. You can go ahead and use 1.005. Now, once you have the Cp, then T2, T1 is all known, so we can easily calculate the compressor work input per unit mass. Same way, turbine work output per unit mass is equal to H3 minus H4, which is going to be Cp times T3 minus T4. We have T3, we have T4. Cp, again, you can surely take 1.005 kilojoule per kilogram Kelvin and solve for it. But here again, what I'm going to do is I'm going to evaluate Cp at T average, which is going to be T3 plus T4 by 2, simply because the temperatures are a bit high and I want to get slightly more accurate number. That's all why I'm doing this. Even if you do 1.005, you're not going to lose marks, so you don't have to bother about it. Okay, so coming back, this is as we discussed, compressor work input is H2 minus H1, Cp average T2 minus T1 if you want it to be more accurate. T average comes out to be 420 Kelvin, which and at this temperature, well, you can do interpolation, or to make matters simple, you could simply take Cp at 400 Kelvin as given in the table, comes out to be 1.00 or 1.013. Now you can see this number is as expected, it's higher than Cp at 300 Kelvin. So it's going to change the compressor work input slightly. It's going to be slightly higher. So when you put this quantity CP average times delta T, we get 246.5. So this is compressor work input per unit mass. Same way, you got to calculate the turbine work output per unit mass, and that's CP average T3 minus T4 or CP T3 minus T4, both work out. Now here, especially the average temperature is a bit higher, yeah. So the average temperature from 3 to 4 is 1043 Kelvin. And just for simplicity, we are going to take CP at 1050 just to avoid interpolations, right? It comes out to be 1.148. Now, this is where actually the difference becomes slightly larger as compared to just taking CP of 1.005 at 300 Kelvin, right? If you took that, the work output from the turbine would be something like 513 or 514, something like that. So it's going to be much, much smaller, right? So again, both methods are fine. I'm just doing this just to be more accurate, nothing else, okay? So now this is the turbine work output. This is the compressor work input. Both are quantities per unit mass. Backwork ratio is simply compressor work in by turbine work out. So 246.5 by 588, you get 41.8 or 42%. That's the backwork ratio, okay? Easy, solved. Once you do this, then we got to go back and look at the thermal efficiency. Okay, now thermal efficiency, you can calculate it in several ways. I think the easiest way is because we have already calculated the compressor and turbine work output, what we can do is W net by Qn. So we could simply take it as turbine work output minus compressor work input divided by Qn. So here all we need to do is to calculate Qn because we already have these two quantities. Now Qn again is simply Qn per unit mass, let's say. The heat addition happens only from 2 to 3. So we are talking about H3 minus H2 or Cp T3 minus T2. Now here again, you can, the same story continues. You could simply take 1.005 kilojoule per kilogram Kelvin, or you could take CP average, okay? Just to be a little bit more closer to reality, nothing else, okay? Now, here, for the purpose of this calculation, I'm going to take CP average, but eventually, once you calculate Qn, you have Qn per unit mass in here, and everything, you have all the numbers. Just put in the numbers in here, substitute the numbers, and you get the efficiency. Okay, so now let me show you that. So here, all we need to do is calculate Qn. As I said, I'm just taking CP average with a CP at T average here. Temperatures are a bit higher, so it's 921 Kelvin, and CP at this temperature, again, to avoid interpolation, I'm doing 900 Kelvin. I don't want to add unnecessarily complications. So simple process. And when you take 900 Kelvin, comes out to be 1.121 kilojoule per kilogram Kelvin, much higher than 1.005. Okay. And when we substitute that CP average times delta T, the Qn comes out to be 848. Now, all we need to do is to calculate the efficiency. So it's turbine work out per unit mass essentially by compressor work in per unit mass by Qn per unit mass. And these are the numbers we calculated. And when you substitute them in, you get the efficiency 40%, 40.3 or 40%. All right. So you can see this efficiency is reasonably high, but this can go up to about 65% if we were to combine the cycle with a steam cycle, which is what is done in combined gas turbine cycles. So this is it. This is the end of chapter 2. We will move on to the next chapter in the next class and see you again.